Hi everyone. So let's start. Now in this lecture we will study theorems for countable set. We have seen what is countable set, what is uncountable set, the three definitions of countable set, that also we have seen. Also we have seen what is Cantor's diagonalization proof. Okay, so a lot of concepts we have seen in this countability. Now our next chapter, that is theorems for countable sets. Okay, so let's start this. So first of all, you already know what is a countable set, what is uncountable set. These definitions you already know. So for example, let's assume you have a set S. Then when can you say this set is countable? What is the definition of countable? What is the definition of countable infinite? What is the definition of countable infinite? And what is the definition of finite? Tell me. If you have a set S, then what is the definition of countable, countable infinite, and finite? So you can see the definition of countable, that is, I can say the cardinality of S that is less than equal to cardinality of N. Okay. Countable infinite means cardinality of S that is equal to cardinality of N. Finite means cardinality of S is strictly less than cardinality of N. So these are the definitions. Yes or no? Agree? These are the definitions. You can easily notice. Okay. Remember, in a countable, I can say there exists a injective function. There exists a injective function. There exists an injective function from S to N. There exists an injective function from S to N. Okay. What is the definition of countable infinite? What is the definition of countable infinite? That means there exists a bijective function. There exists a bijective function between S, N. Okay. And what is the definition of finite? What is the definition of finite? Tell me. That means there is an injective function, but there is no bijective function. Yes or no? There exists injective function. There exists injective function from S to N. Okay, but remember, there is no bijective function. There is no bijective function between S, N. So these are the definitions that we already know. Okay, these definitions we already know. You already know all these things. What is the definition of uncountable? When can I say the definition? What is the definition of uncountable? When can I say S is uncountable? Tell me. When can I say that set S that is uncountable? Uncountable. If and only if set S is uncountable, if and only if it is not countable. Yes or no? If and only if S is not countable. Uncountable simply means that it is not countable. Okay, I can also say that this is uncountable. When can I say that this set S is uncountable? If and only if cardinality of S that is strictly greater than cardinality of N. Yes or no? This is the definition. Cardinality of S that is strictly greater than cardinality of N. There is another definition. What is that? I can say S is uncountable if and only if S is infinite. S is infinite. S must be infinite and no bijection with N. Yes or no? And no bijection with N. There is no bijection with N. So this is the idea. So this is the definition of uncountable set. Okay. Also we know what we know. Also we know that countable set that is the lowest level of infinity. This countable infinite. Yes or no? We know that countable infinity. This countable infinite set. Okay. This is the lowest level of infinity. This is the lowest level of infinity. Correct? This countable infinite set. This is the lowest level of infinity. Okay. And what we call this lowest level of infinity, what is the symbol? How do we denote this lowest level? Denoted by this lowest level. This is denoted by LF null 0. LF null. Yes or no? This is denoted by something like this symbol. LF null. LF null. Yes or no? This is the symbol, or I can say LF0. This is the symbol, right? Yes or no? So this lowest level of infinity, that is your countable infinite set. That is your countable infinite set. Okay, so on the lowest level, what you have? So let's assume this is your LF null. This level. This is the LF null. So tell me, what you have here? This is the LF null. What you have here? You have your natural numbers. Yes or no? You have integers. You have all the rational numbers. You have positive rational numbers. Yes or no? You have n cross n. You have sigma star. Agree? All these we have seen, right? All of them are countable or not? Tell me. All these are countable or not? Yes or no? All of them, these are countable, right? Correct. We have already seen sigma star is countable infinite. N cross n, that is countable infinite. We have already seen set of rational numbers countable infinite. Set of integers, set of positive rational numbers, sigma star. All these things, these are countable infinite. Yes or no? All of them, these are countable infinite. So that you already know. This is the lowest level of infinity. Okay. So we have seen all these things. Remember this lowest level of infinity. So far what we have, lowest level of infinity. So far, what do you know? What you have on the lowest level of infinity? This lowest level of infinity, this is your countable infinite sets. This is your countable infinite sets. Okay. And this is denoted by, this LF0, LF null. This is the symbol LF null. Okay. Now what you have on this lowest level of infinity, on this level, what you have? Tell me. On this level, what you have? On this LF null, you have natural numbers. Okay. You have integers, you have rational numbers, you have positive rational numbers, you have sigma star, you have n cross n. Let me know anything else that we have seen. Anything else that we have seen? Set of finite subsets of n. Yes or no? Set of finite subsets of n. Set of finite subsets of n. Agree? This also we have seen in the previous lectures. Finite subsets of n. So all these things, these are countably infinite. All of them are countably infinite, right? Okay, yes or no? You can see the cardinality is same. This is the lowest level. You can see this is the lowest level. All of them are here. Okay, the cardinality is same. The cardinality of n, that is same as cardinality of integers. That is same as cardinality of rational numbers. That is same as cardinality of sigma star. That is same as cardinality of n cross n. All of them, they have same cardinality. Okay, they have same cardinality as positive rational numbers. Okay, so this is what we have seen. All of them, there exists a bijection. Yes or no? For all of them, there exists a one-to-one correspondence. You can put them in one-to-one correspondence. All of them. Okay, we can put in one-to-one correspondence. All of them we can put in one-to-one correspondence. All these things we have already seen. Okay. Also, we have seen that countable. If you have a countable set, you can put all the elements in a sequence also. Yes or no? We have seen this, that if you have a countable set, then you can put the elements of this set in a sequence where repetition is allowed. Yes, correct. So you can see a set is countable if and only if there is a sequence in which every element of X appears at least once. So this is the idea. A set is countable if and only if you can put the elements in a sequence where every element of X appears at least once. This is the definition. This we have already seen. This is your definition 2 of countable set. Yes or no? This is our definition 2 of countable set. Definition 2. Okay, now let's move on. Now tell me the answer for this question quickly. Tell me the answer for this question. Is there any infinite set such that, is there any infinite set? I am asking, is there any infinite set? Is there any infinite set such that cardinality of S is less than cardinality of N? The answer is no. Give me the reason. Give me the reason also. There is no such set. Give me the reason. Because this N itself is, remember, this is the lowest level of infinity. Yes or no? N is the lowest level of infinity. Lowest level of infinity. Correct? This is the lowest level of infinity. Yes or no? So if you have an infinite set, which, so there is no infinite set. Remember, there is no infinite set who has less cardinality than N. Okay? Because N is the lowest level of infinity. So very simple. This question we have done. Now, tell me this. This is true or false? Tell me. If set S is such that cardinality of S is less than cardinality of N, then S is definitely finite. Yes, this statement is true. This statement is true. Correct? Okay, very simple. Okay, because this N, this is the lowest level of infinity. So it's like this. Okay, it's like this. See, this is the lowest level of infinity. Here, I can say this is your LF null. This is your LF null, means the lowest level of infinity, right? I can say this is the lowest level of infinity. Okay. Now, on this lowest level, these things are there. Okay. All these things you have here. All of them you have here. Now you can easily notice. So, if something has less cardinality, then what will come here? Then tell me what will come here. If something has strictly less cardinality, if S has less cardinality than N, then that will definitely be a finite sets. Yes or no? Here you will have all the finite sets. Very good, very good. And here the remaining levels, what the remaining levels will be? All these remaining levels, these will be uncountable. All of them, these are uncountable. Yes or no? These are uncountable. Is this clear? These are uncountable. Okay. And remember one more thing. Here, this is your countable infinite. This lowest level is your countable infinite. This is your countable infinite. So what is the countable? Which level is the countable level? This level is your countable infinite. You can notice this lowest level. This is your countable infinite. So which level is your countable? What can you say? Where is the countable? Yes. Okay. If you combine these two, then this will be your countable. This will be your countable. Okay. Is this clear? And the remaining, all the remaining levels, they will be uncountable sets. So anyway, now let's see this question. Tell me the answer for this question. Let me know. If S is a set such that cardinality of S is less than equal to cardinality of N and S is infinite, then what you can say about S? S is countable infinite. Yes or no? Then S is countable infinite. This type of set is countable infinite. Very good. Very good. Excellent. Tell me the answer for this question. All countable infinite sets. All countable sets have same size. All countable sets have same size. This statement is false. All countable sets have same size. This statement is false. For example, you can consider this set. Okay, A, comma B. This set you can consider. Another set you can consider is this. So here you can notice this is also countable. This is also countable. This is also countable. But can you notice they have different size? They have different size. Yes or no? So all countable sets have same size. All countable sets, they have same size. This is wrong. Yes or no? Is this clear? All countable sets have same size. This statement is false. For example, consider this. This is countable. Yes or no? This is also countable. And this phi, this is also countable. Do they have same size? Do they have same size? No, they don't have same size. They don't have same size. Cardinality of phi, that is 0. You can notice cardinality of phi, that is 0. And cardinality of n, that is your LF null. Yes or no? Cardinality of n, that is your LF null. Correct? So you can see. So very simple. All countable sets have same size. This is false. Yes or no? So some students were saying yes. Some students were saying true. What was going in your mind? When you said true, some students have said that all countable sets have same size. Some of you said that it is true. In your mind, countable infinite was going on. Yes or no? In your mind, countable infinite was going on. Read this statement. All countable infinite sets have same size. Is this true? All countable infinite sets. Okay, they have same size. This statement is true. This statement is true. This statement is true. And what is that size? That size is called LF null. Yes or no? That size is called LF null. This size, this is called LF null. Agree? Okay, so you can see all the countable infinite sets, they have same size. And their size is equal to what? Their size is equal to set of natural numbers, set of integers. Okay, their size is equal to set of rational numbers. All these things, their size is equal to set of all strings. So this is the idea. Okay, so all the countable infinite sets, they have same size. Is this clear? Please tell me. Understood? Now let me ask you another question. All uncountable sets, All uncountable sets have same size. This question I'm asking, all uncountable sets, they have same size. Now tell me, all uncountable sets have same size. Is this true or false? This statement is false. This statement is false because that is the reason there are infinite levels. Yes or no? See, this is the lowest level. Here you have LF null, but after that you have infinite levels. You have infinite levels. Yes or no? Infinite levels of uncountable. Infinite levels of uncountable sets. Uncountable sets. This we will prove, don't worry. We are going to prove it in the Cantor's theorem. Okay, infinite levels of uncountable sets. This infinite levels of uncountable sets. We will prove it. We will prove it in Cantor's theorem. When we study Cantor's theorem, in the Cantor's theorem, we will prove it. Okay, is this clear? We will prove it in the Cantor's theorem. We will prove it in the Cantor's theorem. Don't worry. So can you notice all countable infinite sets have same size? Yes or no? Can you notice all countable infinite sets? All countable infinite sets have same size. They have same size, correct? All of them, they have same size. Okay. All the countable infinite sets, they have same size. All of them, they have same size. Whatever you take. Okay. All of them, they have same size. Correct? So this we already know. And that size is equal to LF null. I told you LF null. Okay. Now, the same statement if I make for uncountable infinite set. See, every uncountable set is infinite, right? The same statement if I say for uncountable infinite. Uncountable infinite. Now this statement is false. Okay. So I hope this point is clear. So this statement is true. But remember, this statement is false. Okay. Now let's move on. Tell me the answer for this question. If S is a set such that cardinality of S is greater than cardinality of N, cardinality of S that is greater than cardinality of N, then S is uncountable. Yes or no? Then S is uncountable. Very simple. S is uncountable set. Very simple. Okay. So can you notice this is the definition of uncountable? Is this statement true or false? A set is uncountable if and only if its cardinality is greater than cardinality of N. Yes, this statement is true. This statement is true. Okay. Let's move on. Tell me the answer for this question. True or false? Every subset of countable set is countable. Every subset of countable set is countable. Yes, this statement is true. This is very intuitive, right? If you have a countable set, just think about it. Just think about it. If S is countable, okay, this is very intuitive. If S is countable, okay, if S is countable. Now, if you take a subset, okay, if S, let's assume S is countable. Okay, let's assume S is countable. Now, if you take a subset of S, just think about it. Okay, can I say it will have less number of elements than S? Agree with me? Agree with me? If you take a subset, just think about it. This is very intuitive. This is very, very, very intuitive. If you take a subset, if A is a subset of S, then it simply means the size of A that will be less than equal to size of S. Agree? Yes or no? Size of A, you can see if A is subset of S, this is very intuitive. Very intuitive. Intuitively, you can easily see. Intuitively, you can see. You intuitively just understand that if A is subset of S, A is subset of S, remember, it's like this is A, and this is subset of S. This is subset of S. So in this situation, what I can say? I can say cardinality of A that is less than equal to cardinality of S. Okay. So from here, you can easily notice that A is countable. A is countable. Okay. So quite easy. You can see subset of countable set is countable. This is very intuitive. So this is the result. This is the result. Remember, every subset of countable set is countable. Every subset of countable set is countable. Is this clear? every subset of countable set is countable. Now this is useful. See, this is useful. Tell me, you already know set of rational numbers is countable. We know that Q is countable. We know that Q is countable. So because of this, what will become countable? We know set of rational numbers is countable. This is your set of rational numbers. Okay, we know this. That set of rational numbers, that is countable. Okay, this is your set of rational numbers. Set of all rational numbers. So tell me, using this result, what you can say? Using this result, every subset of countable set is countable. Every subset. So what are the subsets? So what will become? So who will become countable? Automatically, who will become countable? You can notice, can I say any subset of Q? Can I say any subset of Q? Please tell me, can I say any subset of Q? So N becomes countable. Okay, yes or no? And so N becomes countable. You can notice any subset of Q, so N is countable. Who else will become countable? Every subset of countable is countable. And you can see set of natural number, that is subset of rational number. Every natural number is a rational number. Every integer is a rational. Every integer is a rational. So this also becomes countable. What else will become countable? Q plus is subset of Q. So Q plus will become countable. Agree? Yes or no? Okay. Is this clear? What about set of all prime numbers? What about set of all prime numbers? Tell me. We know Z is countable. We know integers is countable, right? Yes or no? We know that integers is countable. Set of integers, we know that is countable. Okay, so any subset will be countable. Every subset will be countable. For example, what about set of prime numbers? What about set of prime numbers? Let me know. What about set of prime numbers? That also will be countable. Countable infinite. That also will be countable. Countable infinite. Yes or no? Okay, is this clear? Please tell me. So I hope you understood all these things, that every subset of countable set is countable. Okay, so now because integers is countable, so you can see negative integers, that is also countable. Z minus, Z plus, all these things are countable. Z minus means negative integers. Here positive integers. Okay, your whole numbers, your natural numbers. Okay, all these things, etc. All these things, these are countable. These are countable. So every subset, remember, every subset of countable set is countable. So this is the result. Very simple, quite intuitive result. Okay. Now let's see the next. Tell me the answer for this question. Every superset of countable set is countable. Every superset of countable set is countable. Is this statement true or false? This statement is false. Can you give me a counter example? Can you give me a counter example? See, you can take N. This is a subset of R, right? Yes or no? See, this is countable. This is countable. We have already seen this is uncountable. We have already seen this is uncountable. Yes or no? Every natural number is real number. Every natural number is real number. We know this R is uncountable. This set of real number, that is uncountable. Okay, we already know. So very simple. Okay, you can also see, for example, Q is subset of R. Q is a subset of R, right? Okay, this set of rational numbers, that every rational number is a real number. Now you can note this is countable, but this is uncountable. Okay, is this clear? Let me know. So quite easily you can do. So I can say this statement is clearly false. Okay, tell me the answer for this question. Every superset of uncountable set is uncountable. Every superset of uncountable set is uncountable. Every superset I'm asking. Every superset of uncountable set is uncountable. Yes, this statement will be true. Again, this is very intuitive. Again, this is very intuitive. Yes or no? If you take a superset of uncountable, you are taking superset of uncountable. So of course, that also will be uncountable. This is quite intuitive. Yes or no? This is quite intuitive. You can easily see. Okay, tell me this point. Every subset of uncountable set is uncountable. What about this? every subset of uncountable set is uncountable. Every subset of uncountable set is uncountable. This statement is false, right? This statement is false. Okay. Can you give me example? Can you give me example? Yes, you can take, for example, R. This is uncountable, right? Okay. For example, this R, this is uncountable. Now you can take a subset. For example, I can give you this subset. I can give you this subset, but you cannot. This is countable. I can give you this subset and this is countable. Okay. So this statement is false. Now let's move on. So finally, these are the things that we have seen. If A is subset of B and B is countable, then what A will become? If A is subset of B, if A is subset of B, this is your subset. This is the symbol for subset. Okay, so tell me, if A is subset of B and B is countable, then A will also become countable. And if A is uncountable, then B will become uncountable. Correct? Agree? Okay, so this is very simple point. Remember, let's assume A is subset of B. Now remember, if this is countable, see, if this is uncountable, then what will happen? If this is uncountable, then what will happen? Then this will also become uncountable, right? This will also become uncountable. Okay. If this A is uncountable, then B also will become uncountable. This is the first thing. But if B is countable, then A will also become countable. Then A will also become countable, right? So this is the idea. Okay, yes or no? You can see if B is countable, then subset of countable is countable. Okay, and remember, if A is uncountable, then superset of uncountable is uncountable. So this is the point. Okay, very simple. Now let's move on. Now let's see a very interesting result, that is union of two countable set. What do you think? If I give you two countable set, their union, can you say that will be countable? If I give you two countable set, can I say their union will be countable? The answer is yes. This is true. The union of two countable set is countable. Okay, if you take the union of two countable set, that will be countable. Can you prove it? We can prove it using Hilbert's Grand Hotel. Do you remember Hilbert's Grand Hotel? In the first lecture we have seen countability first lecture, Hilbert's Grand Hotel. Okay, so we can prove it using Hilbert's Grand Hotel, that two countable set, union of two countable set is countable. See what we have to do. If you want to prove, then what you have to do? First, you have to prove that finite union finite is finite. That is easy, right? Finite union finite. There is nothing to prove. This is very easy, that this will be finite. Agree? Agree with me? Okay. See, this is very easy. Finite union finite, that will be finite. If you have union of two finite set will be finite, right? Finite set, union finite set, that will be a finite set. Okay. So there is nothing here. Now, the main thing, let me tell you the main thing, that is basically, if you have a countable infinite, union finite, can I say that will be countable infinite? Can I say that will be countable infinite? Can I say that will be countable infinite? Means countable infinite, union finite, that will be countable infinite. And the third thing we have to prove, that if you have a countable infinite, okay, so let's see. If you have a countable infinite, or I can denote like this, countable infinite, union countable infinite, is that countable infinite? Okay, so these things we have to prove. Agree with me? See, this is quite intuitive. This is very easy. This is easy. Okay, you can do it. But let's prove these things. These two, let's prove. Let's prove. Actually, the proof is very interesting. So I want to tell you the proof. The proof is actually very interesting. So I want to tell you the proof. Proof using Hilbert's Grand Hotel. This is a very famous proof. So I want to tell you. Okay, but remember, this result is quite simple, right? Yes or no? The union of two countable set is countable. If you take any two countable set, the union will be countable. Okay, first of all, did you understand this statement? Did you understand this statement? First of all, you tell me. Did you understand this statement, that the union of two countable set is countable? Means, for example, set of integers, if I give you like, okay, set of integers union sigma star, set of integers union sigma star, what that will be? That will be countable. Okay, that will be countable. So this is the simple idea. Okay, this is what we want to say. For example, I can say set of integers union n cross n. Union n cross n. That also will be countable. So this is the idea. Idea is very simple, that if you have two countable sets, their union will be countable. Okay, so this is the simple idea. You can also see, for example, if you have n cross n, union sigma star, that also will be countable. The union of countable set is countable. This is the simple proof. This is the simple statement. Now let's prove it. We can prove it using Hilbert's grand total. Okay, so first what we are going to prove? First I'm going to prove, see, this the first thing that I'm going to prove. First let's prove first. Okay, this is the first thing that we are going to prove. Let's prove that if you have a countable infinite, okay, if you have a countable infinite, and if you add one more element, union one more element, then result will be countable infinite. Okay, let's prove it. Remember, Ci means countable infinite. When I say Ci, that means countable infinite. Okay, so let's prove that in a countable infinite, if you add one element, okay, this means one element. If you add one element, then the result is again countable infinite. You can prove it. It's like your Hilbert's hotel. Yes or no? It's like Hilbert's hotel. Correct. So what you will do in a Hilbert hotel? This is your infinite hotel. This is the infinite hotel. What you will do if you want to add one more guest? If you want to add one more guest is coming. New guest is coming. What you will do? New guest is coming in this Hilbert hotel. This is the infinite hotel. Infinite. This is infinite. If a new guest is coming, what you will do? You will simply do this. This is what you will do, right? Yes or no? Shift. Oh, Sarak udhar. You can see when a new guest comes, read this meme. When a new guest comes at a fully occupied Hilbert's hotel, you have a fully occupied hotel. Yes or no? When a new guest is coming at a fully occupied Hilbert hotel, then what the manager will do? Manager to every room. Shift. Yes or no? So this is the idea. Very simple. So this is the simple point. So you can see if you have this Hilbert hotel, see, this is the Hilbert's hotel. In this Hilbert hotel, let's assume, okay, first of all, in this you have countable infinite number of rooms. Countable infinite number of rooms. Can anyone tell me why I can say that it has countable infinite number of rooms? Anyone want to tell me why? See, you know that it has infinite number of rooms. It has infinite number of rooms. This you know it has infinite number of rooms. Infinite number of rooms. But how can you guarantee that it has countable infinite number of rooms? It has infinite number of rooms, but why not? But how can you say it is not uncountable? It has infinite number of rooms, but how can you say that it has countable infinite? But how can we say? Tell me. Let me know. How can we say that it has countable infinite number of rooms? Countable infinite number of rooms. Tell me. Anyone? See, you already know this hotel. This hotel has infinite number of rooms, right? This hotel has infinite number of rooms. But in this infinity, uncountable is also there. Agree? When I say this hotel has infinite number of rooms, then number of rooms can be uncountable also. Number of rooms can be uncountable also. But then how can you say that it has countable infinite? Very good, very good. Because rooms are numbered. How can you say that it has countable infinite number of rooms? Because rooms are numbered by natural numbers. Very good. Very good. Excellent. Okay. Because rooms are numbered. So you can say because. So I can say, remember this Hilbert Grand Hotel. Okay. This Hilbert Grand Hotel has countable infinite number of rooms because, tell me why. Countable infinite number of rooms because rooms are numbered. Because rooms are numbered from, because rooms are numbered 1, 2, 3, 4, and so on, right? Yes or no? Because rooms are numbered like this, means they are numbered by n. Is this clear? Because rooms are numbered by n. Okay, is this clear? When I say HGH, what that means? That means Hilbert Hotel. That means Hilbert Grand Hotel. Is this clear? So very simple. Yes or no? This is simple or not? See, you know that Hilbert has this Hilbert Hotel. This has infinite number of rooms. But when I say infinite, it can be uncountable also. You might be thinking, sir, when you say it has infinite number of rooms, it can be uncountable also. Then how can we say it has countable infinite? Because rooms are numbered. Rooms are numbered. These are the rooms. These are the rooms 1, 2, 3, and so on. So that is the reason. So remember, this Hilbert's Grand Hotel, this has countable infinite number of rooms. Okay. Now in this hotel, if one new guest is coming, then what you will do? Okay, this hotel has these many rooms. These many rooms this hotel has. Now one more guest is coming. Let's assume this hotel fully occupied. This hotel fully occupied. Let's assume this hotel fully occupied plus one more guest. Plus one more guest is coming. Then still we can accommodate. Yes or no? We can accommodate. We can still accommodate. We can still accommodate. Correct. Agree? Okay. So for that, what you will do? Very simple. The idea is very simple. This is the idea. Okay. Just shift everyone to the next room. Shift everyone to the next room. This person will go to the next room. This person will go to the next room. Shift everyone to the next room. Very simple. Yes or no? Okay. So you can just remember this meme. Okay. Oh, sarak udar. So you can see, shift everyone to the next room. This will go to the next room and like this. Okay. They are going to the next room. So finally this room number 1 is empty. Yes or no? Finally this room number 1 is empty. So this new guest will come here. So you can see, this is the idea. Everyone is going to the next room. Everyone going to the next room. Okay. So finally this room number 1 will be empty. Empty for the new guest. You can see empty for the new guest. So that's it. Yes or no? So very simple. The proof is very easy, that countable infinite, if you have a countable infinite union, if you add one more element, then that also will become countable infinite. This we have proved. Okay. But how can you prove the second thing? Countable infinite. If finite number of elements are coming, for example, if 1 million numbers are coming, 1 million new guests, or maybe 1 trillion new guests are coming, 1 trillion new guests are coming, then can you accommodate? Tell me. If finite number of new guests are coming, can you accommodate? Yes, very simple. Okay, see, very simple. You can do that. Very simple. What you will do? This is your Hilbert Grand Hotel. Hilbert Grand Hotel fully occupied. Okay, let's assume Hilbert Grand Hotel fully occupied. Okay. Now plus, let's assume 100 new guests are coming. 100 new guests coming. 100 new guests coming. Can you accommodate? We can still accommodate, right? Okay, we can still accommodate. You can still accommodate. So what you will do if you want to accommodate? What you will do? Okay, the same approach. You shift everyone. Okay, we can still accommodate. What you will do? Just shift nth. Okay, shift n room. I can say person in n room. You can say shift person in nth room to whom? To where? Shift person in nth room to n plus 100th room. N plus 100th room. Agree? Okay, just shift. Remember, shift every person. So what you do? Shift person in nth room to n plus 100th room. That's it. If you do this for all n, okay, remember, you do this for all n. You do this for all n. For all n, you do this. Do this for all n. This is what you do. Then finally, what will happen? Finally, what will happen? Okay, the first n rooms, the first 100 rooms will be empty. Yes or no? First 100 rooms becomes empty. rooms become empty. First 100 rooms, they become empty. Okay, so this is the simple idea that first 100 rooms, they will become empty. So you can put these 100 guests. Okay, so these 100 guests you can put here. Okay, so like this. So this is a simple idea. I hope you understood this idea, right? Okay, so very simple. Now something interesting. Okay, something very interesting. Something very interesting. Now in this hotel, okay, something, okay, interesting. Now interesting things are coming. Now let's assume in this hotel, fully occupied. Okay, this is a fully occupied Hilbert Grand Hotel, fully occupied. This is a fully occupied. Remember, it is fully occupied. Now let's assume countable infinite number of guests are coming. Now let's assume countable infinite number of guests are coming. Okay, countable infinite number of new guests are coming. Is this clear? How many guests are coming? How many new guests are coming? How many new guests are coming? Countable infinite number of new guests are coming. This is already fully occupied. This is already fully occupied. You know, this is your countable. This already is countable infinite. This itself is countable infinite. Now, new guests are coming. Countable infinite number of new guests are coming. Anyone want to suggest, can we accommodate? Can we accommodate? Tell me. Can we accommodate? Can we accommodate? New guests are coming. How many new guests are coming? How many new guests are coming? Tell me. How many new guests are coming? Infinite. Countable infinite number of new guests are coming. Countable infinite number of new guests are coming. Countable infinite number of new guests are coming. So infinite number of countable infinite number of new guests are coming. Can we accommodate? Yes, we can accommodate. We can still accommodate. We can still accommodate. See what we will do. We can still accommodate. What we will do? Tell me what we will do. See, the idea is very simple. Okay. Now, this is your hotel. In this hotel, you have room number 1, room number 2, room number 3, room number 4, 5, 6. See, just look at this. Okay, 7 and so on. This is your hotel, right? Okay, now what I will do? First of all, you tell me, infinite number of new guests are coming. Let's call it set A. Let's call it set A. Yes or no? Infinite number of new guests are coming. Let's call it set A. Let's call it set A. Okay, let's call it set A. So tell me, this set A, do you guarantee this set A? Remember this set A, this is countable infinite. This set A is countable infinite. Yes or no? So tell me, can I say that this cardinality of this set, that is same as cardinality of odd natural numbers? Agree? Do you agree with me that the cardinality of this set, that is same as cardinality of odd natural numbers? Yes or no? Okay, because both are countable infinite. This is also countable infinite. Both are countable infinite. This is also countable infinite. This is also countable infinite. And countable infinite sets, they have same size. They always have same size. Yes or no? Countable infinite sets, they always have same size. They always have same size. You already know this. They always have same size. So tell me one thing. Can I say that if all the odd number rooms are available, if all the odd number rooms are empty for these people, can you put them there? Just think about it. If okay, I'm saying if all the odd number rooms are empty, if all the odd number rooms are empty, can I put these people there? Can I put these people there? Yes. Because the size of this set, that is same as size of odd natural numbers. Okay, size of this set is countable infinite. Size of this set, that is same as size of odd natural numbers. So I can say, so if all odd number rooms are empty, all numbered rooms are empty, just notice, rooms are empty. Okay, this is just a if. Okay, this is just a if. I am saying if all the odd number rooms are empty, then Elements of A can be accommodated, yes or no? Then people of A can be accommodated. Correct? Can be accommodated. Agree? Okay. So what we will do? What the idea? The idea is simple. Just empty the odd number rooms. Our target is this. Our target is to empty the odd number rooms. I want to empty all the odd number rooms. Okay. I want to empty, remember. I want to empty all the odd number rooms. So what I will do? I want to empty this room, this room, this room, this room, this room. They must be empty. Okay. They must be empty. All the odd number rooms must be empty. This is what I'm saying. This room, all the odd number rooms, they must be empty. So tell me what to do. I want all the odd number rooms should be empty. Then what to do? There is some person here. Where to send him? I see there is a person here, right? There is a person here. There is a person here, because this is fully occupied. This hotel is fully occupied. This hotel is fully occupied. So where you will send this person? Very simple. Send him to this room. Okay, send this person to this room. Send this person to this room. Send this person to this room. Basically, send this person to room number 8. Yes or no? Agree? So what I'm doing? Please notice what I'm doing. We are basically sending if you have a person in n number room, this is a person in n number room, then where this person will go? Where this person will go? Tell me. This person who is in the n number room, where this person will go? Tell me. This person will go to 2n number room. Yes or no? This person will go to 2n number room. Okay, you can see. Person 1 going to number 2. This is going to 4. This is going to 6. This is going to 8. And so on. This is going to 8 and so on. So finally I can say n is going to 2n. So can I say all the odd numbered rooms are empty? If you do like this, did you throw any existing person? Please tell me, did you throw any existing person? Simple question I'm asking. Did you throw any existing person? No. We did not throw any existing person. And can you notice, now all the odd number rooms are empty. Okay, now all the odd number rooms are empty. So what we have done? This is what we have done. If you have this person who is in the nth number room, this person who was in the nth number room, okay, this person we have sent to 2nth number room. Okay, this person we have sent to 2nth number room. This is what we have done. Okay, this is what we have done. This was the previous situation. This was the previous situation. And this is the new situation. Okay, so you can see. Finally, I can say, so all odd number rooms empty. Remember, all the odd numbered rooms empty. Now you have all the odd number rooms empty. Okay, now what you can do? Now accommodate A. Now we can accommodate A. We can, yes or no? We can accommodate A. Is this clear? Set A. So this is your proof. I hope you found this proof very interesting. See, this is a very interesting proof. You can see, all you have to do, just make sure that 1 is going to 2. See here, 1 is going to 2, 2 is going to 4, 3 is going to 6, 4 is going to 8, n is going to 2n. You can see n is going to 2n. If you do this, then all the odd number rooms are empty. These rooms, these green, look at these green rooms, green signal. Okay, all the odd number rooms are empty. In these empty rooms, these are the empty rooms. In these empty rooms, you can put the remaining guest, the new guest. The new guest you can put in these rooms. So if countably infinite number of guests are coming, see, notice this, countably infinite new guests are coming. Okay, it is possible to accommodate countably infinite new guests. If countably infinite new guests are coming, so you can accommodate them. All the odd number rooms will be free, and then you can put the new guest there. So this is the idea. So what is the conclusion then? The conclusion that we have seen, that is countable infinite, union countable infinite, that is countable infinite. Or I can simply say that countable union countable. Countable union countable. What is that? Tell me. Countable union countable. What is that? Let me know. Countable union countable. That is countable. Okay, that is countable. So this is what we have seen. Did you like the proof? Using the Hilbert Grand Hotel. Hilbert Grand Hotel. This is the proof. Now something very interesting is coming. Okay, just hold. Okay, see, something very interesting is coming. This is what we have already seen. Okay, this we have already seen. You can read this. Okay, this we have already seen. Now let's see something interesting. Now something interesting is happening. Okay, now one day what happens? Let's assume Hilbert Grand Hotel is, let's assume one day this happens, that Hilbert Grand Hotel is already fully occupied. Hilbert Grand Hotel. Let's assume that is already fully occupied. Let's assume that is already fully occupied. Is this clear? Okay, Hilbert Grand Hotel, that is already fully occupied. You already know Hilbert Grand Hotel, that is countable infinite. That you already know. Okay. Now, tell me, one day what happens? Now, one day, these new buses are coming. Just notice who is coming. Just notice who is coming. New buses are coming. Okay, bus A1, bus A2, new buses are coming. Bus A3. Please notice, one day in front of this hotel, who comes? In front of this hotel, new buses have come. And how many new buses? Countable infinite new buses. Number of buses are countable infinite, and every bus is countable infinite. See, this is also countable infinite. This bus is also countable infinite. This bus is also countable infinite. And total, how many buses are there? And total, how many buses are there? And total, how many buses are there? Countable infinite number of buses. Countable infinite number of buses. One day, these many new guests are coming. Okay. Is this clear? One day, these many new guests are coming. Countable infinite number of buses. Every bus is countable infinite. In this bus, how many people are there? Tell me. In this bus, how many people are there? Countable infinite number of people are there. In this bus, countable infinite number of people are there. In this bus, countable infinite number of people are there. In this bus, countable infinite number of people are there, and so on. Is this clear? These are the buses that are coming. I hope you understood. Okay, so countable infinite number of buses have come. These are the new guests that have come. Okay, these are the new guests. Now can you accommodate? Now can you accommodate? Did you understand the questions? Did you understand the question? Now can you accommodate? Question is this. Is there any way you can accommodate now? The question is interesting, right? Yes or no? The question is quite interesting. Now, see, the question is quite interesting. This is your Hilbert Grand Hotel. Fully occupied. Okay, fully occupied. When I say fully occupied, how many people are already there? When I say fully occupied, how many people are already there? Hilbert Grand Hotel fully occupied. That means already countable infinite people are there. Yes or no? That means already countable infinite people they are there. Countable infinite people are there. Already countable infinite number of people are there. Okay. Now plus new guest. Okay. Plus new guests are coming. Now how many new guests are coming? New guests. These are the new guests. Okay. Set A1, set A2, set A3, set A4, and so on. Remember, this is countable infinite. This is countable infinite. This is countable infinite, and so on. And total, you have countable infinite. Okay, I can say total you have countable infinite buses. Number of buses. Countable infinite number of buses. Now can we accommodate? This is the question. The question is simple. Now can we accommodate? Now can we accommodate? Now can we accommodate? This is the question. Now can you accommodate? And the answer is yes. Again, the answer is yes. Okay. Again, the answer is yes. Can accommodate. Can still accommodate. These many, so many people, we can still accommodate. Okay. See what we are going to do. Notice what we are going to do. This, see, the idea is this. Please notice. The idea is this. What we will do, first you empty all the prime number rooms. Okay. First empty all the prime number rooms. First empty all. What you do? First you empty all odd number rooms. Okay. First you empty all odd numbered rooms. This is first what you do. All odd numbered rooms. Is this clear? This is the first step. See, idea is this. First empty all the odd numbered rooms. Is this clear? Now what you do? Now what you do in, see, now what we are going to do? You tell me, where are the old guests? First empty all odd numbered guests, all odd numbered rooms. So where you will shift all the old guests? Tell me. Shift old guest to even number rooms. Very good. Very good. Even numbered rooms. Even numbered rooms. So this is the idea. So first what you do, see the step one by one. I'm telling you, one by one. I'm telling you, please understand. First you shift all the odd guests to even numbered rooms. Okay, just shift them. Now what is there? Now who is there? Now who is empty? Now all odd numbered rooms are empty. Yes or no? Now all odd numbered rooms are empty. Okay, so this is what you do. Now all odd numbered rooms are empty. Now what to do? Now something interesting I'm going to do. You tell me, before telling you anything, you tell me how many prime numbers are there? What the cardinality of prime numbers means? How many prime numbers are there? Let me know. How many prime numbers are there? That is countable infinite. Yes or no? Very good. Very good. Very good. That is countable infinite. See, set of prime numbers. Set of prime numbers that you already know, that is countable infinite. Set of prime numbers. Set of prime numbers is countable infinite. Is a countable infinite. This you already know. So can I say the size of the number of prime number rooms? Can I say that is same as number of buses? Let me know. Let me know. So can I say that number of prime number rooms? Number of prime numbered rooms. Number of prime numbered rooms. Okay. That is same as number of buses. That is number of buses. Number of buses is same as that. Okay, yes or no? So very simple idea. I hope you understood this. This is the simple idea, because remember how many prime numbers are there? That is countable infinite. Set of prime numbers, that is countable infinite, that we already know. Okay, and you can notice number of buses, that is also countable infinite. Number of buses, that is also countable infinite. So I can say, now the idea is this. What you do? See, the idea is this. All the odd number rooms are empty, remember. All the odd number rooms, they are empty. Now what you do? Where you will put this bus? This bus A1. In which rooms you will put? In which rooms you will put this? Okay. Where you will put this bus? You will put in the room number. In room number what? In room number 3 power. Okay. In room number power of 3. Is this clear? Power of 3. This bus you put in these rooms. Where you will put the next bus? Where you will put the next bus? The next bus you put in the room number 5 power n. Okay. In the room number 5 power n. N greater than equal to 1. Where you will put the next bus? Where you will put the next bus? In the room number 7 power n. N is greater than equal to 1. See, just think about it. Very simple approach. Extremely simple approach. Where you will put the next bus? Where you will put the next bus? Next bus where you will put 11 power n. N is greater than equal to 1. 11 power n. Yes or no? Where you will put the next bus, and so on. And so on. Understood? Did you understand? Very simple, right? Very clever idea. Okay, very clever idea. So that's it. So very simple. So remember, idea is simple. All the odd guests, they will go to even number rooms. Okay, now all the odd number rooms are empty. All the odd number rooms, they are empty. All the odd number rooms they are empty. Now, bus A1, you put in these rooms. Okay, bus A1, you put in these rooms. 3 power 1, 3 power 2, 3 power 3, 3 power 4, and so on. Bus A2, you put here. Bus A3, you put here. Bus A4, you put here. Okay, so very simple. So this is the idea. Idea is simple. Old guest, where they are gone? Old guest gone to even numbered rooms. Old guest, all the old guests, you just put them in the even numbered rooms. Okay, there you put. And where you will put the new guest? Now let's see the new guest. Okay, the new guest you are putting like this. If you have a bus, okay, if you have a bus A1, this bus A1, where you will put bus A1? This bus A1 you will put in these rooms. 3 power 1, 3 power 2, 3 power 3, 3 power 4, 3 power 5, and so on. These are the room numbers. Okay, these are the room numbers, remember. These are the room numbers. This is the room number. These are the room numbers. So these, all of them, these are room numbers. Room number 9, room number 27, room number 81, and so on. Okay, so these are the room numbers. So basically every bus AI, that will go to some prime number. Okay, this bus will go to some prime number. Okay, remember, it will go to some prime number, some prime p power n, where n is greater than equal to 1. I hope you understood. So every bus you can put in these rooms. Okay, is this clear? Let me know. So simple. So this is the idea. I hope you understood this also. So this was the interesting point. So this is the result. Okay, this is the conclusion. See, the conclusion is very simple. The conclusion is this. Can you notice? Countable infinite, union. See, countable infinite, union countable infinite, that is countable infinite, right? This we have seen. Okay, the second, this is interesting, that countable infinite, union countable infinite, union countable infinite, union countable infinite. How many times? How many times? How many times? Countable infinite times. Countable infinite times. Okay, countable infinite times. The result will be countable infinite. The result will still be countable infinite. Okay, the result will still be countable infinite. Understood? Let me know. So this is interesting. This is interesting. Okay, so you can see this union of countable number of countable sets. Union of countable number of countable sets. That is countable. That is countable. Yes or no? Is this clear? So this is the point. See, this is the point. Conclusion. This is the conclusion, that C means countable. When I say C, that means countable. Okay. So finally, I can say countable, union countable, that is countable. The second point, countable, union countable, and so on. And so on. How many times? Countable infinite times. Or I can say countable times. Or I can say countable times. Okay. The result will still be countable. The result will still be countable. So this is the idea. Okay. Union of countable number of countable sets, that is countable. The union of countable family of countable sets. Union of countable family of countable sets, that is countable. Okay. And the proof we have seen, that is using Hilbert Grand Hotel. I hope you found the proof interesting. Yes or no? The proof was quite interesting, and I hope you will remember this always. Very interesting proof, right? Yes or no? Hilbert Grand Hotel. So very easily you can prove it. Okay. So you can read this. This is what we have done, right? The new people, where they are going? The new people are going to prime number power. The new people, new guest, they are going to prime number power. Powers of prime number. Powers of prime number. Okay, let's move on now. Now let's see this question. Intersection of two countable set. What you can say? What you can say? Intersection of two countable set. That is countable. But how to prove it? That is countable. But how to prove it? See, if you have, let's assume you have a set A. This is countable. This is countable. And let's assume you have a set B. This is also countable. Now tell me, what you can say about A intersection B? Tell me, what you can say about A intersection B? Let me know. A intersection B. What you can say about that? What you can say about that? Yes, that also will be countable. Very good. That also will be countable. Okay. See, the proof is simple. So the proof is very simple. You tell me, can I say, let's assume A intersection B, that, can I say that is subset of A? Can I say that is subset of A? Tell me. Tell me. Can I say that is subset of A? Of course. See, this is the Venn diagram. You can create the Venn diagram. This is set A. This is set B. So where is A intersection B? Where is A intersection B? This area is A intersection B. Can I say this area, that is subset of A or not? That is subset of A or not? Yes or no? So tell me, if this is countable, subset of countable is what? Subset of countable is what? Subset of countable. Subset of countable is countable. Yes or no? So I can simply say subset of countable. That is countable. That you already know. That you already know. Subset of countable is countable. Subset of countable, that is countable. So this is very simple proof. I hope you understood. Okay. I hope you understood. The same thing you can say, remember? So this you understood, that if you have set A is countable, B is countable, this you understood that A union B, that is also countable. That is also countable. Okay. That is also countable. And remember, A intersection C, A intersection B, that is also countable. That is also countable. Okay, both are countable. And you can also do this. Okay, there is no need to prove it. That is very easy to prove. But you can see that if you have, for example, let's assume each AI is countable. Let's assume each AI is countable. Okay, let's assume each AI is countable. Okay, assume each AI is countable. Assume AI is countable for all I belonging to N. Okay, is this clear? Okay, means AI is countable. AI, that is countable. Okay, let's assume. Then in this situation, every AI is countable. Every AI is countable. Like, for example, I can say A1, A2, A3, and so on. Okay, so this is also countable. This is also countable. This is also countable. And remember, I belongs to natural number. So ultimately, how many times this is? I belongs to natural number. So how many times this? So how many times? So countable infinite times. Yes or no? So I can say countable infinite times. Infinite times. Countable infinite times. Okay. So very simple. So finally, you tell me, if you do their union of AI, what that will be? That also will be countable, right? That also will be countable. And what will be their intersection? What will be their intersection? Intersection of AI. That also will be countable. Intersection of AI also will be countable. Now, something interesting you have to remember. See, here I can say countable infinite also. But can I say countable infinite here? In the intersection, can I say countable infinite? See, this is correct, but this will be wrong. But this will be wrong. Focus. See, we know that CI, countable infinite, union countable infinite, that is countable infinite. This we know. We know countable union countable is countable, that we know. We know countable intersection countable is countable, that we know. But what about this? Countable infinite, intersection countable infinite. What about this? What about this one? Please tell me. Think about it. Think. What about this one? This may or may not be countable infinite. See, this will be countable, right? Yes or no? Okay, this will be countable. See, if you have countable infinite, intersection countable infinite, that will be countable. There is no problem in that. There is no problem in that. But this may or may not be countable infinite. This will be countable, but this may or may not be countable infinite. This may or may not be, I can say this may or may not be countable infinite. Okay, can you give me counter example? Give me counter example. For example, consider this. See, consider this set of integers. Okay, you can just consider, for example, you can consider set of negative integers, intersection set of positive integers. Yes or no? Set of negative integers. This is countable infinite. This is countable infinite. What is their intersection? What is their intersection? Their intersection is 5. This is not countable infinite. But yes, this is also countable. See, this is also countable. This is also countable. Correct? Okay. So this is the idea. Okay. Another example. Give me another example where countable infinite intersection countable infinite is countable infinite. For example, this. What is their intersection? Their intersection is Z. This is countable infinite. This is countable infinite. This is also countable infinite. This is countable. Is this clear? Please tell me. So in the intersection, you have to take care. You have to take care. Okay. So remember, simple point. If you have countable intersection countable, that will be countable. Countable intersection countable. That will be countable. There is no problem in that. Okay. Countable intersection countable is countable. But remember, countable infinite intersection countable infinite. Okay. That may or may not be countable infinite. That may or may not be countable infinite. But of course, this will be countable, right? This will be countable. Because countable intersection countable is countable. This will definitely be countable, but this can be finite also. But this can be finite also. Okay, so these things you already know. Now, so finally I can say the union and intersection of countable set is countable, right? The union intersection of countable set is countable. Union of two countable set is countable. Intersection of two countable set is countable. We have seen this. What about Cartesian product? Let me know. What about the cross product of two countable set? If you have two countable set, what about their cross product? Cartesian product of two countable set. That will be countable. But how to prove it? But how to prove it? Tell me. Let me know. The Cartesian product of two countable set is countable. The Cartesian product of two countable set is countable. For example, n cross n. This we have seen that this is countable, right? We have proven. This we have already proven. This is countable. We have already proven to be countable. To be countable. Agree? Yes or no? So this we have already proven to be countable. This is what we are saying. The Cartesian product of countable sets is countable. How to prove? See, the proof is very simple. See, let's prove it. Okay, prove it. The proof is again the snake type of structure you can create. See, snake type of structure you can create. Okay, just create the snake type of structure. For example, if you have this set A, let's assume this is countable. Okay, this set A, this is countable. Let's assume this set A, let's assume this set A is countable and these are the elements. Okay, A2, A3 and so on. This is the set A. Let's assume you have set B also. That is also countable. Okay, you take two countable sets. This is what I'm saying. Okay, take two countable sets, B2, B3 and so on. Tell me what their intersection, what their Cartesian product. What their Cartesian product will be? That will contain ordered pairs. Yes or no? That will contain ordered pairs. First element will come from A, second element will come from B. First element coming from A, second element coming from B. First element coming from A, second element coming from B. First element coming from A, second element coming from B. First element coming from A, second element coming from B. Okay, first element coming from A, second element coming from B. So like this. Okay, A3, B3, and so on. So like this, dot, dot. Okay, you can just dot, 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 dot. Okay, correct. So this is your Cartesian product. Now prove that A cross B is countable. What you will do? Now prove that. Okay, so what you can do to prove, what you need to prove? You need to prove A cross B is countable. A cross B is countable. This is what you need to prove. So what you can do? Okay, what you can do? You can just create the sequence. Okay, just create enumeration. Just create enumeration. Just create enumeration of A cross B. Okay, just create the enumeration of A cross B. That's it. So what you can do? See, this A cross B, this you can write like this. Okay, here you what to do? Here you write where A1 is the first element. Okay, where A1 is the first element, you write like this. Please notice. Where A1 is the first element, you write like this. When A1 is the first element. This is how you write. Okay, in the second row, what I will do? In the second row, when A2 is first element. When A2 is first element, in the second row, you put. In the second row, when A2 is first element. In the third row, when A3 is the first element. Is this clear? Let me know. This is what you do. Just first you arrange, basically. First you arrange all the elements. A3, B4, and so on. And then finally, A4, B1. First you arrange all the elements. In the fourth row, A4 is the first element. And so, tell me how many rows will be there? How many rows? Countable number of rows. Yes or no? Number of rows, that will be size of A. Number of rows, that will be size of A. Number of rows, that will be size of A. Number of columns, that will be size of B. Yes or no? Tell me. See, number of how many rows will be there? That is your size of A. And how many columns will be there? How many columns? How many columns will be there? That is size of B. Yes, agree. Now tell me. Now create the enumeration. How will you create the enumeration? I want to create the enumeration. Give me the enumeration. So the enumeration of A cross B. Enumeration of A cross B. So for that you can create a snake structure. You can just create this snake structure. Okay, just create this snake structure. Means first you do this, then you do this, then you do this, and so on. Okay, see what you can do. First you do this, just go like this, snake structure. First you write A1, B1. Then what you do? Then you write these two. Then what you will do? Then you will write these. Okay. Then what you will do? Then what you will do? Then you will write these. Then you will write these. Okay. And so on. I hope you understood. Okay. So I hope you understood. So basically we are going like this. This is what we are doing. See, very, very simple. Like this, we are going like this, like this, like this. Okay, like this. Notice, like this, like this, like this. So like this. Okay, we are covering all the elements. Like this, if I do, will we cover all the elements? Will we cover all the elements? Will we cover all the elements? Tell me. If I do like this. Yes, very good. So we will cover all the elements. So the enumeration is like this. You start with A1, B1. You start with this pair A1, B1. Then what you do? Then you write A2, B1, A1, B2. Then you write A2, B1, A1, B2. Then what you write? Then what you write? Then you write A1, B3, A2, B2, A3, B1. Okay. A1, B3, A2, B2, A3, B1. And so on. Dot, dot. Okay. This is your enumeration. This is the enumeration. Okay. Very simple. So because you have enumeration, so I can say, so A cross B is countable. So A cross B, that is countable. Is this clear? So if A comma B are countable, then A cross B is also countable. So this is the result. Now let's move on. Let's move on. So you can see the Cartesian product of finite family of countable set is countable. Okay, remember this point, that you have countable cross countable, that is countable. If you do countable cross countable, that also will be countable. As long as you are doing finite number of times. How many times? As long as you are doing finite number of times. Finite number of times. Please understand. Finite number of times. As long as you are doing finite number of times, there is no problem. Finite number of times, as long as you are doing, there is no problem. The result will be countable. Okay, is this clear? Okay, the Cartesian product of finite family of countable set is countable. So remember, countable cross countable is countable as long as you are doing finite number of times. Okay, if you are doing only finite number of times, then the result will be countable. What about if you do countable infinite number of times? Something interesting. True or false? This statement, is this true or false? Countable, see, Cartesian product of infinite number of countable set is countable. Cartesian product of infinite number of this infinite. When I say infinite, this can be countable or uncountable. Okay, remember, when I say infinite, it can be countable infinite or uncountable. It can be countable infinite or uncountable. Or uncountable. When I say infinite, it can be any of them. Now I'm asking, Cartesian product of infinite number of countable sets is countable. Is this statement true or false? This statement is false. Can you give me an example? We have already seen. Can you give me one example? We have already seen. Do you remember set of all infinite length strings that is uncountable? Do you remember? See, do you remember that set of all infinite length binary strings? Infinite length binary strings is uncountable, right? Yes or no? That is uncountable, correct? Agree? Set of all infinite length binary strings. If you take set of all infinite length binary strings, okay, that is uncountable. This we already know. Now, can you notice? If you notice one thing, this sigma, okay, this sigma, let's assume sigma is 0,1. Let's assume. Okay, let's assume your sigma is 0,1. Now tell me, if I do sigma cross sigma cross sigma, and let's assume I keep doing this countable infinite number of times, or maybe infinite number of times. If I keep doing this infinite number of times, when I say infinite, it can be countable infinite or it can be uncountable. This I told you. When I say infinite, it can be countable infinite or it can be uncountable. So if I do this infinite number of times, what I will get? This set, let's call this set S. So I will get this set S, yes or no? I will get this set S, agree or not? Is this clear? Please tell me. This is your infinite length strings. This will create infinite length strings, agree or not? Please tell me. Sigma cross sigma cross sigma cross and so on. Infinite number of times. This will create infinite length strings or not? Sigma cross sigma and so on. Infinite number of times. This will create infinite length strings. This will create your set S, and that is uncountable. Understood? Please tell me. Did you understand? Let me know. Okay. Is this clear? Please tell me. So remember this point. These are some important points that if you do this, notice countable, union countable, union countable, union countable. If you do this countable infinite number of times, then that is fine. Yes or no? Union is fine. if you do this countable infinite times, then the result will be countable. The result will be countable, right? Yes or no? Okay. Is this clear? The result will be countable. But notice that if you do cross product, countable cross product, countable cross product, countable cross product, if you do this countable infinite times, if you do this or infinite times, either you do this countable infinite times or you do this uncountable times. Okay, basically, if you do this, please understand, if you do this countable infinite times or you do this uncountable times, then the result may or may not be countable. Is this clear? The result may or may not be countable. May or may not be countable. The result may or may not be countable. Is this clear? Please tell me. Okay, if you do this, the result may or may not be countable. But for union, it is fine. For union, it is fine. For cross product, this is fine. If you do countable cross product, how many times? Finite number of times if you are doing. If you are doing finite number of times. Okay, if you are doing finite number of times, then that is fine. That will be countable. Okay, so we have already seen everything so far. Are you comfortable? Please tell me. Tell me the answer for this question. Let me know the answer for this question. True or false? Cartesian product of infinite number of finite sets. Cartesian product of infinite number of finite sets is countable. This statement is also false. The same counterexample, sigma is 0, 1. See this sigma cross sigma cross sigma. See, this sigma was finite, yes or no? This was finite. This was finite, finite cross, finite, and so on. If you do this infinite times, what it will become? What it will become? This will become uncountable, right? This will become uncountable. The same example. Is this clear? Please tell me. Did you understand? Let me know. Cartesian product of infinite number of finite sets. Infinite number of finite sets. That is countable. That is false. Clear? This example you can take. So remember, this is the simple point. If you have finite, cross finite, how many times? If you do this infinite number of times, then result may or may not be countable. Okay? Then the result may or may not be countable. Is this clear? Let me know. Is this clear? The result may or may not be countable. Okay? So all these examples, everything we have seen. Now you can see these three theorems. Are you comfortable? These are the fundamental properties of countable set. If A, B are countable, every subset of countable is countable. This is clear. Every subset of countable is countable. Countable union countable is countable. Countable cross countable is countable. So these we have already seen. Okay, let's move on. What about these two? See this. Let's assume A is non-empty set. If there exists injection from A to countable set, what you can say? See, this is an interesting question. The question is quite interesting. So tell me. See, this is the question. Read this. If there exists injection from A to countable set. Okay, this is the question. Remember, the question is this. A is non-empty. So far, we already know that A is non-empty. A is non-empty set. Now the question is saying that there is injection from A to countable set. Okay, let's assume B is countable. And there exists injection. Okay, there exists injective function. there exists injection. You can see there exists injection from where to where? From A to B. There exists injection from A to B. You tell me, if there exists injection from A to B, what that tells you? What that tells you about the size? What that tells you about the size? If there exists injection from A to B, you have injective function from A to B. What that tells you about the size of A and size of B? Size of A, size of B. Very good. Size of A is less than equal to size of B. Very good. Size of A that is less than equal to size of B. Okay. So if B is countable, subset of countable is countable, right? So from here, can I say, see, if B is countable and the size of A is less than B, see, A may not be subset of B. A may not be subset of B, but you can see size of A is less than size of B and B is countable. Size of A is less than size of B and B is countable. What you can say from here? Can I say A is also countable? Agree or not? Yes, agree. So this is the simple point. Now let's see the next one. The next. If there exists a surjection from countable set to A. Okay. Now what happens? Let's assume set A is non-empty, set B is countable. Now the question is saying there exists a surjection. Now the question is saying there exists a surjection. Okay, the question is saying there exists a surjection. From where to where? Tell me, surjection is from where to where? Surjection from where to where? From countable set to A. Surjection is from B to A. Surjection is from B to A. If surjection is there from B to A, what that tells you? There exists a surjection from B to A. What that tells you about the size of A comma B? What that tells you about the size of A comma B? I can say size of B is greater than equal to size of A. Now you can see B is already countable and size of A is less than size of B. Size of A is less than size of B. Size of A is less than equal to size of B. So automatically A will be countable. So these are interesting statements. Yes or no? Did you understand? Please tell me. These are interesting. These are very simple. You can see if there is injection from A to countable set, then that will be countable. A will be countable. If there is surjection from countable set to A, then A will be countable. Okay. So very simple. These are the statements we have seen. Okay. So these statements are true. Let's move on now. So we have seen everything. There is nothing we did not see. See, the set of positive rational number is countable infinite. We have seen. Yes or no? We have proven. This we have already proven. The set n cross n is countable infinite. We have proven. Next, A1, A2. These are collection of countably many countable infinite set. Countably many countable infinite set. So their union will be countable. So their union will be countable. This also we have seen. Everything. All these three statements we have seen. We have already seen. Let's see the next one. Let's see the next one. We have seen this, yes or no? N cross n is countable. This is your n cross n. This is countable. We have seen this. Already we have seen. The set S of all infinite binary sequences is uncountable. This also we have seen. Agree? This also we have proven using Cantor's diagonalization. The set of all infinite binary strings, that is uncountable. This we have proven using Cantor's diagonalization argument. Okay. This also we have seen. The set of real numbers is uncountable. We have proven it using Cantor's diagonalization argument. Let's move on. Tell me the answer for this question. Tell me the answer for this question. Let me know. Tell me the answer for this question. Try this question. Is Q minus N? Is Q minus N that is countable or uncountable? Q minus N. First to tell me about Q minus N. See, can I say Q minus N that is subset of what? Q minus N that is subset of what? Q minus N that is subset of Q, right? See this array, just create the Venn diagram. Just create the Venn diagram. This is Q. Okay. See, this is the Q. This is your Q. and this is your n. This is your n. So where is q minus n? This is your q minus n, right? Okay, correct. This is your q minus n. This is the q minus n. You can see this is subset of q. Okay, so tell me, countable. This is countable. Subset of countable is what? Subset of countable is what? Subset of countable, countable. Subset of countable is countable. Subset of countable is countable. Agree? Subset of countable is countable. So I can say this will be countable. Is this clear? So q minus n, that will be countable. Is this clear? Please tell me. This statement will be countable. Understood? Yes or no? Okay, so far, so we have done this. This we have done. So you can see this will be countable. Okay, what about the next one? What about the next one? What about r minus z? What about r minus z? What about this? R minus z. How can you prove that r minus z is uncountable? You are saying r minus z is uncountable. This is what you are saying. But how can you prove that r minus z is uncountable? How will you prove? Let me know. How will you prove? Give me a proof. You are a Go classes student. You should prove. You have clear understanding. Now you can prove also. Which method you will apply? 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 Tell me. You can apply the proof by contradiction also you can apply. Proof by contradiction also you can apply, right? Yes or no? You can apply proof by contradiction. Okay? So just apply proof by contradiction. Proof by contradiction. Proof by contradiction. So tell me, how will you prove it by contradiction? How will you prove it by contradiction? See, very simple point. What is r minus z? See, can I say r minus z? Okay, let's call it just, okay, let's call it, for example, let's call it some s. R minus z, let's call it s. So tell me what your r will be. If r minus z is s, remember, you already know this is your z, this is your r, this is your r. Okay, now tell me, this is the r minus z. This area is r minus z. So tell me, let's assume r minus z is s. Okay, let's assume r minus z is s. So what I can say about r? Very good. R is s union z. S union z. Now prove by contradiction. Now can you prove by contradiction? If s is countable, then r will be countable. Yes or no? If s countable, then what will happen? Tell me. If s countable, if this s is countable, then what will happen? Tell me. Then r countable. Then r countable. And that is contradiction or not? Let me know. R countable, that is contradiction or not? You are getting this. Okay, is this clear? This proof, this is a very interesting proof. See, okay, let's generalize this. Let's generalize this. Let's do the generalization. Okay, see, this is the question. Let's assume this set A. You have two set A, set B. Let's assume this is uncountable. Okay, see, let's generalize this. Take your copy pen. Let's do it. This is set A, this is uncountable. And let's assume set B, that is countable. Now, from uncountable, if you remove countable, what you will get? A minus B. What you can say about it? From uncountable, you are removing countable. What you can say about it? The answer is this will be necessarily uncountable. Yes or no? This will be definitely uncountable. Okay, this will be definitely uncountable. And we can prove by what? We can prove by contradiction. We can prove it by contradiction, right? Correct? Let's prove it by contradiction. Let's prove it by contradiction. So tell me what your proof will be. Let's prove by contradiction. Means uncountable A, this is your uncountable A, minus countable B, minus countable B. I am saying the result will be uncountable. The result will be uncountable. Okay, this result will be uncountable. This is what I am saying. So prove by contradiction. What your proof will say? Proof is like this. Assume A minus B is countable. Yes or no? This is proof by contradiction, remember. So this is proof by contradiction. Assume, what you do? You just assume A minus B is countable. Is it countable? Okay, just assume that it is countable. Let's call it S. Let's call it S. Okay, let's call it S. So tell me, this is your, like you can create the Venn diagram. Just create a Venn diagram. Just create a Venn diagram. This is A. This is B. So tell me, what is S? Which area? Which area is A minus B? This area is S, right? Correct? This area is S. So now tell me, what I can say about A? What I can say about A? So A will be equal to what? A will be equal to what? Let me know. A will be equal to what? This area. You cannot, this area is S. Now what A will be equal to? So here, for this area A, so that will be equal to what? I can say that will be S union A intersection B. Correct? Agree? Agree or not? Yes or no? Tell me. S union A intersection B, because this is A intersection B. Please notice, this is A intersection B. This area is A intersection B area. See this area is A intersection B area. Okay, that you already know. This area is A intersection B. A intersection B. This is the A intersection B area. You tell me one thing. You tell me one thing. A intersection B, how can you say this is countable? I am saying this is countable because this is subset of B. Yes or no? This is subset of B. Agree or not? Agree or not? See, A intersection B, that is subset of B or not? That is subset of B, because this is your A, this is your B. Now this area, look at this area. This area is A intersection B. This area is subset of what? This subset of B. And B is already, this is already given to you countable. This is given to you. So tell me, subset of countable is what? Subset of countable is what? This is given to you that it is countable. So subset of countable is what? So A intersection B is countable. So A intersection B, that is countable. A intersection B, that will be countable. So finally, this is what I'm saying, that this is countable. This is countable. Okay. And if you assume this is countable, okay, remember you are assuming, yes or no? You are assuming that S is countable. If you assume this is countable, so what will happen? Countable union countable. What that will be? Countable union countable. That will be countable. So A is countable. Isn't that a contradiction? Isn't that a contradiction? It is given that A is uncountable. Okay. A is countable. This is a contradiction. This statement has created a contradiction. Is this clear? Interesting proof, right? Simple proof by contradiction. Simple proof by contradiction. This is the contradiction. I hope you understood. So tell me, understood? Let me know. Did you understand? Please tell me. So this is your proof by contradiction, because we got a contradiction. Okay. Because we got a contradiction. So what should happen? So what should happen? So remember, this is the conclusion. This is the conclusion, that from uncountable, if you remove countable, what you will get? You will get uncountable. From uncountable, if you remove countable, you will get uncountable. Clear? From uncountable, if you remove countable, you will get uncountable. This is the final result. Okay, so what about this R minus Z? That will be uncountable. that will be uncountable. R minus Z, that will be uncountable. Okay, simple. So what about set of irrational numbers? From this, you can also say, what about set of irrational numbers? Set of all irrational numbers. Tell me, what about set of all irrational numbers? Set of all irrational numbers, that is countable or not? Irrational numbers. Set of all irrational numbers, that is uncountable. How to prove it? So what is the proof? How to prove it? What is the proof? See, the proof is simple, because what is the set of irrational numbers? Let's call it S. What is S? That is R minus Q. R minus Q. Uncountable minus countable. What is that? We have already seen uncountable minus countable is uncountable. Yes or no? Uncountable minus countable, that is uncountable. That is uncountable. Agree? Yes or no? Please tell me. So set of all irrational numbers, that is uncountable. Because remember this, uncountable minus countable is uncountable. The proof, did you understand? Did you understand the proof? Proof by contradiction. Proof by contradiction. Did you understand the proof? Proof by contradiction. Okay. So this result you can use. You can use this. Uncountable minus countable will be uncountable. See, this is intuitive also, right? Do you agree with me? This is intuitive also. You have uncountable. This uncountable is very big. This is another level. Uncountable is very big. This is another level of infinity. From this level, if you remove this level, it does not change. Yes or no? From this level, this is another level of infinity. Uncountable, this is another level of infinity. From this level, if you remove countable, this is the lowest level of infinity. This is the lowest level of infinity. If you remove, then you will again get uncountable. So this is intuitive also. Okay, tell me the answer for this question. Let's solve this question. Tell me the answer. X is an uncountable set. X is uncountable set. If one-to-one correspondence is there, then what you can say about A? See, X is uncountable. X is uncountable. X is already uncountable. And you have one-to-one correspondence with uncountable. See, this X is uncountable. This is uncountable. And you have one-to-one correspondence with uncountable. Then what is your size? This is uncountable. And you have one-to-one correspondence with this. You have one-to-one correspondence with this. So from here, if one-to-one correspondence is there, that means set A size is equal to set X size. Can I say? Can I say? Because there is one-to-one correspondence. You have one-to-one correspondence. So set A size is equal to set X size. Correct? Okay? Yes or no? Very simple. So you can see, because there is one-to-one correspondence, so set A size is equal to set X size. So A is uncountable. So this A, so this is also uncountable. Uncountable. Okay, so simple point. Now let's see the next one. Tell me the answer for this question. Let me know the answer for this question. C is countable subset of uncountable set. C is countable subset of uncountable set. What you can say about X minus C? That will be uncountable. Very good. That will be uncountable. Remember, uncountable minus countable is always uncountable. Okay, we have already seen this. We have already proven it. This proof we have seen. So remember, you have uncountable X. You have uncountable X. So notice, you have uncountable X minus countable C. Minus countable C. The result will be what? The result will be uncountable. Because uncountable minus countable is uncountable. So this is your another question. Tell me the answer for this question. This we have already seen, right? Sigma is any finite set. Then set of all sequences of finite length means set of all finite length strings, that is countable. Means sigma star is countable. Sigma star is countable. This is the simple point. This we have already seen that sigma star is countable. Agree? Okay. So you can see sigma star, that is countable. Set of all strings, that is countable. Finite length strings, okay, that is countable. We have already seen. We have proven. We have proven already. Okay. Let's move on now. Now let's see some more questions. I just want to ask you some quick questions. This is a rapid fire round. Okay. You can consider this as a rapid fire round. Some results about uncountable set. Rapid fire. So tell me the answer for this. Uncountable union countable. Uncountable union countable. See, uncountable union countable, that will be uncountable. Very good. That will be uncountable. Very good. What about this one? Uncountable union uncountable. Uncountable union uncountable, that will be uncountable. Okay. Uncountable union anything, right? Uncountable, if you add something more, if you add something more, that will be uncountable. Okay. Tell me the answer for this. Uncountable minus countable, that will be uncountable. Okay. What about this? Uncountable minus uncountable. Uncountable minus uncountable. This may or may not be uncountable. Yes or no? This may be uncountable. This may not be uncountable. This may or may not be uncountable. This may or may not be uncountable. Give me something. Give me uncountable. See, give me this scenario. Give this scenario. Give situation. Okay, give me uncountable minus uncountable equal to countable. Give me this. Give me this. Uncountable minus. Tell me, anyone want to give me this? Uncountable minus uncountable is equal to countable. Very good. Real minus rational. Very good. Very good. Uncountable means real. Okay. Uncountable means irrational. You remove all the irrational number. The result will be what? The result will be rationals. The result will be rationals. Okay. Now give me this. Now give me this. Uncountable minus uncountable is uncountable. Give me this also. Uncountable minus uncountable is uncountable. Give me this also. Please tell me. Anyone? Uncountable minus uncountable is uncountable. Anyone? Very good, Mayuk. Very good. Very good. Very good. See, you can just take rational numbers minus, you remove these. See, you can take real numbers minus these. These are also uncountable. Real between 0, 1. These are reals between 0, 1. We have proved it. These are reals between 0, 1. We have proved that this is also uncountable. So real minus this, that is also uncountable, right? Yes or no? See, this is your real line. This is the real line. On this real line, we have already seen this. This we have proved, if you remember. If you remember, we have proved this range itself is uncountable. This range itself is uncountable. Okay. So now you just think about it. If I remove this range, still the result will be uncountable, correct? Yes or no? So you can see, if I remove R minus, if I remove this range, then that also will be uncountable. Okay, that also will be uncountable. So this is the point. So you can see uncountable minus uncountable, that may or may not be uncountable, right? Yes or no? That may or may not be uncountable. So this is the idea. Okay. Now, one more thing I want to tell you here. In the real line, if you take, see, if you take a real line, okay, this is interesting that if you take any two reals, okay, this, remember, if you take for any two different reals, for any two different reals, you can take any two different reals. For any two different reals A, B, remember this range from A to B, this range is uncountable. Okay, this range is uncountable. means you can take any two different reals. Okay, if your A is here, let's assume, your B is here, let's assume. As long as they are different, then this range, the between them, this range will be uncountable. You can take any two A comma B. For example, you can take you can take A as 0.1 and you can take B as 0. You can take B, you can take C. What you can do, I am saying, you can take A as 0.01 and you can take B as 0.1. Between them also, this range is also uncountable. Is this clear? Because this is the real line. This is the real line. So you can take any two different numbers. See, you can take any two different numbers, whatever two different numbers you take, A, B, as long as they are different. A must be different from B. As long as they are different, this range on the real line, this will be uncountable. If you remember, we have proven, what we have proven? Do you remember we have already proven that this range 0 to 1, if you remember, we have proven this range 0 to 1, this is uncountable. Similarly, the same thing here also, as long as A is not same as B, they are different, then the range between them, that is uncountable. Okay, so this is just a small point. Now let's move on. Tell me about this, countable minus countable. Rapid fire again. Rapid fire starts again. Countable minus countable, that is countable, very good. What about countable minus uncountable? Countable minus uncountable, that will be countable. Okay, because see, okay, why? See, if you have countable A and if you have countable B, then result will be what? Then result will be A minus B. And that is subset of A or not? Yes or no? See, the result will be A minus B. That is subset of A. That is subset of A. And subset of countable is what? Subset of countable is countable. Subset of countable is countable. Agree? Subset of countable is countable. Subset of countable is countable. So you can see countable minus uncountable. Remember, that is countable. Okay, that is countable. So this will be countable. Countable minus uncountable, that will be countable. Okay, so these things we have seen. Tell me the answer for this one. If S is uncountable and, okay, let's assume S is uncountable. Okay, S is uncountable. If S cross A is countable, then what is A? Think about it. S is uncountable. If S cross A, Cartesian product, if S cross A is countable, what is A? What is A? Very good. Very good, very good, very good. Devans, Raj, very good. Okay. So this A will be phi. Very good. Here you can notice the only option is A is phi. Here A will be empty set. Because just think about it. Just think about it. Your A is uncountable. Okay. Simple, think about it. A is uncountable. Now, if you take B is non-empty, then if B is non-empty, you can take any B. If B is non-empty, what will be A cross B? Just think about it. Just think about it. If B is non-empty and A is uncountable, then the size of this will be greater than equal to size of A. Agree? Yes or no? Okay. So from here you can notice A cross B will be uncountable. Will be uncountable. Will be uncountable. Now the only possibility, but if you take, for example, if A is uncountable and B is phi, this is the only possibility where A cross B will be phi, which is countable. Okay. Is this clear? So this is the result. Uncountable cross non-empty set, that will be uncountable, right? Yes or no? Uncountable cross non-empty set, that will be uncountable. Okay. So we have seen everything. This is your, I can say, theorems about countable sets, uncountable sets. Are you comfortable? Union of countable sets is countable. Cartesian product of two countable set is countable set. Intersection of countable set is countable set. Uncountable minus countable is uncountable. All the things that we have seen, all the questions that we have seen in this session, we have done a lot of questions. A lot of questions we have done. Some nice results we have seen. Some nice proof we have seen. Please tell me, are you comfortable with countable, uncountable? This chapter, has it become, I can say, very easy for you? Please tell me. Very easy for you. This countable, uncountable. Countable, uncountable, all these things. This chapter, has it become very easy for you? Now, in the next lecture, we will see Cantor's theorem. We will see infinite levels of infinity. Infinite levels of infinity. This Cantor's theorem we will see. Then we will see all the GATE exam, TIFR exam, NET, ISRO, NILIT, all these questions. Okay. Please tell me. Comment your feedback on the YouTube. Okay. On the YouTube, I have uploaded countability lectures. Please comment your feedback on the YouTube. Okay. Put your feedback in the comments. Let me know. Are you finding this countability very interesting, very easy? Okay. These things, very easy, very interesting. And are you comfortable that, okay, whatever question will come in the GATE exam, any variation they ask me in the GATE exam, I can solve, I can handle. Whatever they ask, I can solve, I can prove also. If some set is given to you and they ask, prove that it is uncountable, I can prove using Cantor's diagonalization proof. Okay. And if some set is given to you and they ask, prove that it is countable, then I can prove using definition 3, definition 2, definition 1. Okay. So a lot of things we have seen. I hope you are comfortable with countability. Okay. So please comment your feedback on the YouTube. Okay. So in the next session, we will see this important theorem, Cantor's theorem. This theorem we will see, and then all the previous year exam questions we will do. Okay. Okay. Thank you, everyone.